The mouse has a mass 0.15 kilograms and the spring extends by 20 centimeters when the mouse is supported vertically by the spring. Calculate the frequency of oscillation of the mouse if it is set into oscillation on a low friction horizontal surface. Here we need to find the frequency of oscillation, and the information we are given is the mass of the mouse and how much the spring extends when the mouse is supported vertically. So that's giving us the case when you have the spring vertically and the mouse is attached at the end. So say that's the equilibrium position, the extension is 20 centimeters. This is what we found in the first part of the question, and that may be useful to answer this part. I'll just keep that there. But we need to go to frequency from these values that we have, mass and the extension. So we need to somehow relate those quantities to each other, which is not really something you can do with just one equation. But if we start with the frequency and see what we can write for that, and we'll see how that these can be included and we get a value for frequency. So the first thing you can think about frequency is probably it's 1 over the period. That's one relation you have, which is not really helpful in this case because we don't really know the period either. But the period is 2 pi over omega. So I can say this, which when you flip the fraction there, it becomes omega over 2 pi. Well, this is slightly better now because we have got omega involved in, which we can actually relate to these quantities. How is that relation? Well, now we need to look back to this one, what we found in the first part. It says that for this particular mouse on the spring, the acceleration is minus k over mx. But we know that the standard SHM equation, the equation for simple harmonic motion, is A is equal to minus omega squared x. Now we can compare these two. So we have got the accelerations. Remember, this is the general form, valid for all SHMs, and this is for this spring and mass. We have the accelerations, we have the x values, displacement from the origin, and these are the ones which are different. So, but since this is valid for all SHMs, we can say that omega squared is equal to k over m. Well, that's useful because we have got the omega there, so which we can get from this relation. We can say that omega is square root of k over m. And that gives us a way of finding omega. 2 pi is a constant, which means we can find the frequency once we find the value of omega. But how do we find omega? Well, we know the mass, that's fine, that's given 0.15. then it's K that we are interested in now. For K, we will go back to these pieces of information given, because 0.15 kilograms will be used in there, but we haven't used the 20 centimeters at all, so that must have some use somewhere. And going back to this diagram, this is a slightly different diagram than what's going on with the mouse. This is the mouse supported vertically, and it's giving you the extension 20 centimeters with this setup, but the extension is related to the force on the spring, which we already wrote before. The relation is F is equal to the magnitude of the force will be K times X, the extension. The X there is this 20 centimeters. But what's the force? Well, the force acting in that case is the weight of the mouse. That's pulling it down. We have got 0.15 G, and then there is the force from the spring pulling it up, and since they'll be in equilibrium, these two forces will be equal to each other. So we can put this force equal to K times X, because this force of the spring, this is the force of the spring there, is equal to 0.15 G, because the mouse is in equilibrium, they must be equal to each other, and that's the weight pulling the mouse down. The spring will pull with the same force up. So we can say 0.15 G is equal to K. This is the spring constant that we are trying to find, times the extension, which is 0.2 meters. Rearranging this, dividing by 0.2 on both sides, we get that the value of K is 0.15 times 9.81 over 0.2. That gives you 7.4 newtons per meter. And we can take that K and put it in the K there, which will give us our omega value. So omega will be square root of 7.4 over, the mass was 0.15, and that is 7.0 radians per second. Finally, we can take this omega and put it back in there, our original frequency equation. So we can say, therefore, the frequency is 7.0 over 2 pi, which is 1.1 Hertz.